Let's look at another example. Suppose we want to figure out whether the integral from 0 to 1 over x squared dx converges or diverges. And of course the problem here is at 0. 1 over x squared goes to infinity at 0, but it's continuous elsewhere on the interval from 0 to 1. We simply follow the definition. It says that the integral from 0 to 1 of 1 over x squared dx is the limit as t approaches 0 from the right of the integral from t to 1 of 1 over x squared dx. And of course, for any t bigger than 0, this integral is defined because the function 1 over x squared is continuous on the interval from t to 1. And now we can find an antiderivative for 1 over x squared. It's minus 1 over x. And we're looking at the limit as t approaches 0 from the right of minus 1 over x evaluated at 1 minus that evaluated at t. So it turns out to be the limit as t goes to 0 from the right of minus 1 minus 1 over t. And as t approaches 0, 1 over t approaches infinity, and this entire limit approaches infinity as t approaches 0 from the right. So therefore our improper integral, the integral from 0 to 1 of 1 over x squared dx, diverges. So recall before we had the integral from 1 to infinity of 1 over x squared converges. Now the integral from 0 to 1 of 1 over x squared diverges. And again, it's not very difficult to show the general result for 1 over x to the p. The integral from 0 to 1 of 1 over x to the p is divergent if p is bigger than or equal to 1 and convergent if p is less than 1. Note that 1 over x is divergent in both cases from 0 to 1 and from 1 to infinity. Otherwise, the behavior of the integral of 1 over x to the p switches when you switch the interval from 0 to 1 to 1 to infinity. And you'll see later in the course when we get to p series that this will be a very, very important result for us, and it'll explain our obsession with the integral of 1 over x to the p.